Okay, today we're going to demonstrate how an action potential works chemically and physiologically inside of a neuron. Perspective, this is a neuron. This is the dendrite, which receives stimulus. This is the axon that passes through the cell body, and this is the terminal end of the axon that would release a chemical to the next dendrite, and so on and so forth. You can see that the key here, p to the negative exponent, if you will, represents the negatively charged proteins. So at the beginning, or at rest, the neuron is actually very, very negative. It has a very high number of negative millivolts, about negative 70 at rest. And that's because there's far more negatively charged proteins than these positively charged potassium ions. However, there are lots of positively charged sodium ions outside of the neuron, in the space outside of the axon, and that will play a large role in generating an action potential and sending an electrical charge down the end of the neuron. So, at rest, before the neuron is stimulated, you can see that the relative number of sodium ions outside of the neuron is far greater than those inside. However, upon being stimulated, but before these channels open up, the sodium channels, small numbers of sodium ions move into the neuron, but enough of them move into the neuron that the potential of the charge differences between the two sides of the neuron starts to rise, and it starts to become more and more and more positive inside of the neuron. Now, I probably want to scooch this back just a little bit. So, as you guys all learned earlier, at about negative 40, or negative 50, from the original resting potential of negative 70, this is enough of a charge difference, or what we call threshold, to allow more sodium ions to enter, and they're passing through a now open voltage channel, which facilitates or allows more sodium ions to come in. So as more and more and more sodium ions enter in through the channel, the environment becomes progressively more and more positive and overwhelms, if you will, the negatively charged proteins, again represented by capital P. So as more and more and more come in, we start to get higher and higher electrical charge, and we reach a peak. So this surge of sodium ions into the neuron creates an action potential. So an electrical impulse passes through down the length of the axon. However, just like a toilet can't flush until it refills and gets ready to flush again, the neuron can't generate another action potential and send another electrical charge until it regulates, or it balances the charge. Now, at about plus 50 millivolts, this generates an opening of the potassium voltage channel, which then starts pumping ions out. In this case, the potassium ions start to get pumped out of the neuron and starts to create a more and more negative charge. So the action potential continues by creating a more and more negative charge well below the resting potential of minus 70. Now, at this point, in order to help facilitate the balance as well, a sodium and potassium pump also helps facilitate this. So more and more sodium ions are pumped out of the neuron, and more potassium ions are pumped back in to create more and more negative charge. Because even though some positively charged potassium ions are coming in, making the inside environment more positive, more and more sodium are being pumped out to create an overwhelmingly more negative environment. Whoops. inside due to the negatively charged proteins. So more and more of these are pumped out. And it's just arbitrary as long as you remember that there's more more negatively charged proteins than positively charged potassium. You'll realize that the electrical charge inside of the neuron is at about -70, meaning that it's ready to be stimulated again and send another action potential down the length of the neuron. Now, even though I've only shown 3 different gates here, the sodium and potassium gate and this pump here, there are several of them down the length of one neuron.